Okay, so we're going to have a look at this checklist. All right, and so I'll just discuss the skills quickly, the questions, revision resources, and then we've got some questions on the back that I want to go through because these are going to be a good summary of questions to expect in the test and make sure we're all pretty comfortable with those skills and so forth. So firstly, our test is this Thursday. That's our plan. Make sure we're ready for that. 51 marks at the moment, but I'm still altering the mark scheme. I haven't written the test. We'll have about 65 minutes. You can bring 1 page of handwritten notes and you will have your graphics calculator with you. So then if we just look at the skills, basically they correlate with the chapters there, you know, so 2A, add, subtract and multiply polynomials, 2B is finding zeros. But we can just break it down into a series of skills. So I'd expect you to be able to read those dot points, know what that means, and then be able to do that, okay? And if you can do that, if you do all of these things, you'll be able to get 100% in the test. Okay, so I'll leave the skills for you guys to have a read through. Just as far as the revision resources go, you might remember right at the end of last lesson, I was talking about the tests. So the 2018, 19, 22 and 23 tests are both functions and polynomials. For the other years, they just did it on functions, so they're relevant, and then complex numbers for 2017, 20 and 21 have some relevant questions. So I've given you guys the 2018, 2019, 22 and 23 test. So if you want more printed, let me know. We got some exam revision questions. They're in your notes book right at the end. Recommend having a look at those with solutions on the OneDrive. And there's some more questions and so forth in the OneDrive folder. All right, any questions about the conditions and content and so forth? All right, let's rip straight into these questions then. So we've got some revision questions that we're going to go through together, just so I can point out a few skills and how we can use our calculator and so forth. All right, we have P of X is a polynomial, it's a cubic, x to the 3 plus 2x squared plus ax plus b. And we have, when it's divided by x take 2, the remainder is 4. It is also known that x take 2 is a factor. All right, so we're applying both here the remainder theorem and the factor theorem. So the remainder theorem says if x plus 2 is a factor, is a remainder, when it's divided by x plus 2, the remainder is 4. What this means is p of minus 2 equals 4. Okay, that's what the remainder theorem means. So we're going to plug minus 2 into p of x. That will give us minus 2 to the 3 plus 2 times minus 2 squared. Take 2a plus b, and that equals 4. And we'll simplify this for an expression just in terms of a and b. So we'll have here minus 8. That'll be 4 times 2 plus 8. So minus 2a plus b equals 4. That will cancel. Okay, so we've applied the remainder theorem there. All right, the factor theorem. If x take 2 is a factor, what that means is p of 2 equals 0. All right, so we're going to put p of 2 in now. We'll have 2 to the 3 plus 2 times 2 squared plus 2a plus b. So this gives us 8, this will give us 8 plus 2a plus b. So we'll have 2a plus b equals 16. All right. Now we will...
Is it negative 16 or just regular 16?
Negative 16. Yeah, good pick up. Now, we've got a set of simultaneous equations here, right? And so we need to bring them together somehow. You can solve it by elimination, you can solve it via substitution. It's completely up to you. Elimination is probably the easiest way. Like if we just add these equations together, I can see that's going to cancel. So I'll have minus 2a plus 2a, that part will cancel. b plus b, that'll be 2b. And 4 plus minus 16 will be minus 12. We'll get b is minus 6. And if b is minus 6, well then minus 2a take 6 equals 4. So minus 2a equals 10, a equals minus 5. So we've got b and we've got A. Okay, so what did we do with this question? We applied the remainder theorem, okay, and we got a simultaneous equation involving A and B. We applied the factor theorem, we got another one, and then we just solved them by elimination. We added the equations together, we got the value of B, solved through, got the value of A. All right, pretty happy with that? So then, part B says to fully factorise the cubic. So we won't go through this whole one, but I'll just set it up for you to show you how we can fully factorise the cubic. So we know, we're told that x take 2 is a factor. That means x take 2 multiplied by some quadratic. All right, so I'm going to put in here, I'll put the whole general quadratic for now, ax squared plus bx plus c. That's going to equal this cubic over here, x to the 3 plus 2x squared, and we solved A, take 5x, and we solved B, take 6. Okay, that's, so we're going to find that quadratic factor and then factorise the quadratic using a completed square method. And you can already see, okay, x times ax squared, that's going to give you that x to the power of 3 value, so A has to be 1, all right? And we can also see that C has to be positive 3 because minus 2 times 3 is the constant term and that has to be minus 6. And so then we're down to finding one term and we can do that via expansion, determine the value of B by equating the coefficients. And then to graph, you can either use, you have the roots here or we can use our calculators to support us there. Okay, any questions about number 1? Really good. Let's move on to 2 then. And we have this graph here. All right, very good. Part A says graph the modulus of f of x. All right, so this is the function, and here we're going to put the modulus of the function. Now, all the modulus means is every negative y value becomes positive. So it's just going to go like this. Okay, we just flip that component, we make it positive, and so that's going to be our function, the modulus of f of x. Okay, part B, we have the f of the modulus of x. Okay, and what we do with this one is we discard the function for values of x less than 0. So we have this part existing, okay, that part there, and then that part is just mirrored in the y-axis. So that's going up there like that. That's our modulus, f of the modulus of x. Okay, now for C, C is going to be a little bit more involved, and we might open up our notebook to have a look so that I can remember how we do this. 1 on f of x. So one way you could do this is just by variable interchange, right? You know, so you can approximately determine the coordinates of this point here. All right, this point here has a x coordinate of -1 and a y coordinate of positive -1. All right. So if we go 1 divided by f of x, we're going to be doing 1 divided by the y value, -1, 1 divided by -1, which means it has the same y value at that point. Okay, but I will point out in our notes book for this one. So if you go to reciprocals of other functions, which is 3f, okay, because we will have one like this. Now, in the test, right, you're just getting marks for drawing the graph, okay? So you don't have to rationalise the whole process of it. I would expect you to be able to do that skill. But one thing you could really easily do, probably the best way to do it, would be to find the equation of this quadratic and then just graph 1 on that quadratic in your calculator and copy it. Because that'd be really easy, right? You can see the roots here are 0 and, what's that one, 2. Put the piece of paper down, -2. So we would have a times x take 0 times x plus 2. They're the roots. X times x take x plus 2. And then we can determine the a value by putting that coordinate in. We can find this equation fairly easily and just graph that. Nonetheless, let's go through the theory. So we have, it's not 3e, it's 3d, sorry, reciprocals of other functions. All right, so let's go through these dot points and see which ones apply. Zeros on the function become asymptotes, okay? The zeros on this function become asymptotes on this function, which means we have an asymptote at 0 and an asymptote at 2. And that's the case because if this is a 0, we would have 1 divided by 0, and we have undefined at that point. All right, let's scroll down. There's no vertical asymptotes on this one, so we don't need to worry about that. We don't have a local max, but we do have a local minimum here. Local minimum, so I'm reading the 4th dot point now, page 20 of our notebooks. Local minimum becomes local maximum, all right? So this local min becomes a local max. So what we have going on there is this kind of thing. And we know the coordinates of that point as well, all right? When x is minus 1, y is minus 1, because we have 1 divided by that y value. Okay. Then we have, when f of x approaches infinity, 1 on f of x approaches 0. So what we can see going on here, past 0, this function is approaching infinity. Okay, it's getting closer and closer and closer to infinity, which means this function is going to get closer and closer and closer to 0 because we have 1 divided by infinity, and we've got the asymptote there, so we can anticipate this shape. And the same in the left direction as well. It's approaching positive infinity here, so 1 divided by positive infinity approaches 0. That's what the 1 on f of x shape is going to look like. All right, cool. I think we did a couple of those when they popped up. Okay, so that's question 2. Let's go to question 3. So we have, consider the function x to the 3, x squared take 3x take 4 on top of x plus 2. So this is a rational function. It's a function expressed as a ratio. We have one function divided by another. Part A, determine the roots of the equation and the vertical asymptote. So for a rational function, u on v, okay, the function equals 0 when u equals 0. So that's when the roots occur, and we have a vertical asymptote. We have an asymptote when v equals 0. All right, so the top part then, for the roots, x squared take 3x take 4 equals 0. We can factorise this, minus 4 and plus 1. So they're the x values of the roots. And then the asymptote will be minus 2. Asymptote only has one s. Asymptote x is minus 2. Very good. Okay, part B. Determine the equation of the oblique asymptote. So I said this is going to pop up. If you graph this function, it's going to have some kind of shape like this. And there's this asymptote here that both sides of the function are approaching. Bad sketch. Okay, so there's this asymptote, oblique because it's not a vertical, it's not horizontal, it's the equation of a line. And we've just determined this via a division process. Okay, so we're going to divide this quadratic by this linear factor, and you can use the division algorithm, you can use synthetic division, it doesn't matter. All we're looking for is the final answer, which is what's the equation of the oblique asymptote. So we've got x plus 2 is our divisor, and this is our polynomial. All right, so we start by asking ourselves, what do I multiply by x to get x squared? Just x, isn't it? X times x will give me x squared. X times positive 2 will give me plus 2x. Subtract it away. Minus 3 take 2 will be minus 5x. Okay, and what do we multiply x by to get minus 5x? Minus 5. Form that. Minus 5 plus 2 minus 10. And then subtract that away. That will cancel. minus 4 plus 10 is 6. Okay, so we have the polynomial on top of the divisor. I'm going to write it two ways for you. X squared take 3, x take 4 on top of x plus 2 is equal to the quotient. This is our quotient plus the remainder on top of the divisor. Okay, so just look right at the bottom of the page there for question 6. See how we've got the two ways we can express a polynomial? We need to fix b a little bit. So that should say p of x on d of x. So 6b, right at the bottom, it should say p of x on top of p of x. So if we have a polynomial on top of a divisor, all right, here we have a polynomial on top of a divisor, it's equal to the quotient plus the remainder on the divisor. If you graph both of these polynomials, you'll see that they're the same. Now, as x approaches infinity and negative infinity, all right, let's just focus on this component. We have that's going to infinity, 6 divided by infinity is going to 0. This component is approaching 0, and so we're left with the equation of the line x take 5. Basically, our quotient is the equation of the oblique asymptote. So to answer part B, determine the equation of the oblique asymptote, y equals x plus 2. X take 5. All right, so we've done a few polynomials and a few functions there. Everyone pretty happy so far? Excellent. All right, question 4 then. Now we have a composite function here. We have the function is sine x, and the g function is root x, and we're asked to find g of f of x. So we're putting f of x into g of x, g of f of x. G of x eats f of x, and we would have the square root of sine x. Now, it might be good for us to talk about domain and range here as well. So that's not one listed, but here's the function. Let's discuss domain and range quickly. So the domain of this function, all right, so the possible values of x that it can take, this component has to be positive, and sine is positive between 0 and pi. All right, so we can have the square root of 0, so we would include that point. All right, the square root of sine of any of these values will give you a positive number. And then plus k2 pi, okay, where k is an integer. That will allow for every possible domain of sine of x. And then the range, all right, the largest sine can be is positive 1, all right, and the lowest it can be is 0. So we'll have between 0 and 1. Okay, so that will be the domain and range of this function. If you were to graph it, it's going to look something like this. Alright, so it's existing between 0 and pi, and intervals of that. Okay, let's answer the question it wants us to do. Find all solutions, okay, all values such that g of f of x equals 1. So if we have the square root of sine of x equals 1, we'll square both sides. Sine of x is 1. And when is sine of x 1? It's when we'll have to look at our unit circle here. There'll be one of these questions pop up. Pi on 2, and then plus k2 pi for k in d. Okay? Now, it says find all values. So that gets you the sort of third mark. This process here is getting you the first two well, this is probably only worth 2 marks in this one. The one in the test is a little bit harder, but same kind of concept. Okay, 5. All right, so we've got 3x plus 4 on 2x take 1. The first part says graph. Let's graph it on our calculators and talk about it. Here's mine. Now, whenever you're doing a graph in a test, right, you need to make sure you do it properly. Like graphing, you're just copying, all right? And it's easy marks to get. And I always say you've got to make sure you get the easy marks and you just try get the hard marks, okay? But you make sure you get the easy marks. So if we look at this function, I'm just going to provide a rough sketch of it, but I'll talk about in a test situation and exam from now on, we will always give you the axes, okay, to draw on, which means we'll always give you a V window, all right? And so whatever V window we provide you with on the axes here, that's the one you put into your Cartesian plane. You make sure you label your axes, you make sure you label the function, you make sure you note any important points such as intercepts, maximum and minimum, asymptotes, both horizontal and vertical. Now we can see here that we have a vertical asymptote at half. Okay, so we've got that one going on there. And we have a horizontal asymptote as well at 3 on top of 2. One and a half. All right, and then the function has this shape. All right, and we can put the roots on there and the y-intercept just by jigsawing and so forth. Okay, that's part A. Part B, explain why the function has an inverse function. Explain why f of x has an inverse. Now, whenever you're asked to do this, there's only 3 words you need to write. F of x is 1, 2, 1. All right, so if a function has an inverse, remember 1 to 1. You know, f of x is 1 to 1 in that each x value has one unique y value, and each y value has one unique x value. It passes both the horizontal line test and the vertical line test. All right, remember the vertical line test to determine whether it's a function, the horizontal line test to determine whether it's a function that we can perform the inverse of. Okay, part C. Find f of minus 1 of x using variable interchange. So, if our function is, I'm going to write it like this, y equals 3x plus 4 on 2x take 1. In order to perform variable interchange, what we do is we swap x and y. So we'll have x here, and we'll have 3y plus 4 here, and 2y take 1 here. All right. Now, we're gonna try and solve this to get y by itself. So what I'm going to do, I'm going to move this term up here. We'll have x times 2y take 1 equals 3y plus 4. All right, and we want to get the y's on one side basically and the x's on the other. So we'll distribute this here. We'll have 2xy take x equals 3y plus 4. We'll move this y term over to the left and this x term over to the right. 2xy take 3y equals x plus 4.
Is swapping the variables f of x and negative 1 of x? Is that why you swap variables?
Variable interchange? Yeah. Yep. So where it says using variable interchange, what we do, that's why we swap x and y in this step. Cool. All right. So now we've broken it down. We've got y is a common to both of these terms. We'll factorise that there, and we're left with 2x take 3, and then we'll divide both sides by 2x take 3, and we have the equation of the inverse function. All right. Part D, determine the domain and range of f of x and f of minus 1 of x. All right. So if we just think about f of x first, all right, its domain is going in that direction forever and that direction forever, but it doesn't exist at x is positive half. Okay, so for the domain of f of x does not equal half. And for the range, all right, it goes down forever and up forever, but it doesn't exist at 3 and 2. So y does not equal 3 or 2. And then for the inverse function, okay, the inverse function, it just swaps, doesn't it? The domain of the inverse function, so I'll list that here. Domain is x does not equal 3 or 2. And the range, y does not equal. And you can observe that from your graph, but also that's a property of inverse functions, is that the domain of f of x becomes the range of f negative 1 of x. Very good. Okay, last one. So here we've got a polynomial division, and this is where I installed that software on your calculator, and I said we can use software to support us. So I would expect you to be able to perform this division. So we have a quartic. We have x to the 4 plus 3x squared. So if we were going to perform this division, we would write it like this, right? X squared plus 2x take 3, that's the divisor, and we're dividing the polynomial x to the 4 plus 0x to the 3. Don't forget, if there's none of that coefficient, we chuck a big 0 there, plus 3x squared, take 2x plus 3. Okay. And then we go through and perform the division algorithm process. Okay. So, we are asked to state it in two ways. Firstly, like this. Alright, and then secondly, like this. So just familiarising you with both ways of stating the polynomial. So on your calculator, let's follow these steps. We're going into program. So we go menu, program, and you have one there called polydiv plus. Polydiv plus. Alright, so we press execute to open that program. Alright, numerator order. So if you think, let me write it out, what are we doing? We're doing x to the 4 plus 0x to the 3 plus 3x squared, take 2x plus 3, divided by, and this quadratic, x squared plus 2x, take 3. Okay, numerator order. What's the order of the polynomial at the top? 4. The highest power is 4. So we just type in the number 4, press enter. Okay. Enter all numbers coefficients in order from highest to lowest power. Okay, so the coefficient of x to the 4 is 1. So we press 1 and press enter. Okay, the coefficient of x to the 3 is 0. So we press 0 and press enter. 2 is the number 3, enter. The coefficient of the x term is minus 2, enter. And the constant term is positive 3, enter. Okay, so we enter the whole numerator. Has everyone followed along so far? Yep, I'll make sure you can do this on your calculator.
I'm behind.
Oh, right. Are you happy to
I'll do this again later. Like,
this skill?
Catch up.
You sure?
Yeah.
Yep, alright. How about you guys? Yep.
Yeah, just don't.
Oh, you typed it all in already?
Yeah, don't
excellent. All right, so
display.
you've flown ahead. You're just too fast for me. All right, so denominator order is 2. So it's very intuitive, isn't it? You know, so we've got 1, 2, minus 3. And this is the order in which it displays it to you. Okay, so it's going to produce a matrix for you. The numerator's at the top, the denominator's in the second row, and so we're particularly interested in the quotient and the remainder, right? We already know what the polynomial is, we already know what the division factor is, so I'll evaluate that. And so the third row, okay, I've got the number 1, the number minus 2, and the number 10. So that means my quotient is x squared, take 2x, plus 10. Okay, one lot of x squared, take 2 lots of x, plus 10. That's my quotient. I've got that from the third row. My divisor is this one that we started with up here, x squared plus 2x take 3, and the remainder is that term hanging out at the bottom, minus 28x plus 33. Alright, so that's one way we can state the polynomial. Alright, the alternative way of presenting it, if we have the polynomial on top of the divisor, we would have the quotient, which is this one, x squared take 2x plus 10, plus the remainder on top of the divisor. Now, if you graph this function, and you graph p of x on d of x as this function, you'll see that they are the same. Okay, so I'm not saying this function and this function are the same, I'm saying this function and this function on d of x will be the same as this one. Alright, cool. So that's a pretty thorough recap of everything that we've got in the test. Yeah, what do you guys reckon?